welcome to our kinetic molecular theory notes. The kinetic molecular theory is a way of describing gas behavior. We will be referring to gas particles when we talk about things in this kinetic molecular theory. A gas particle can be thought of in terms of its behavior as a tiny hard sphere, almost like a bouncy ball, if you will. Or kind of like a small marble. What is in between the particles, we really just consider to be nothing, just kind of empty space, or a vacuum. Gas particles can exist as one of three things. They can exist as individual atoms. This would be the case in the monoatomic gases that we call the noble gases, neon, argon, things like that. So you have just one kind of single particle there, or one single atom there. We can also expect them to be diatomic gases, things like hydrogen, oxygen, or Hanoch-Klipperith, if you will. And we can also consider them to be actual molecules of a compound, so water vapor, CO2, something like that. All of these behave essentially the same, even though their geometry isn't exactly the same, so we really consider them to just be gas particles. The kinetic molecular theory is indeed a theory. It's a model that is trying to explain how gas particles behave. There are four major parts to this. Some of them work better than others. So there are flaws to this, but in most cases it works. So there are going to be what we call deviations from this, where we'll say, oh, the theory isn't working so well for that. But overall, the kinetic molecular theory does a pretty nice job at describing how gases behave. There are certain gases that behave in the most ideal fashion. So ideal gases don't really exist. Okay, so there is no example of an actual ideal gas that follows these rules perfectly. When we talk about an ideal gas, it's kind of like this idea of talking about an ideal kid. Every single kid breaks a rule from time to time, but there are some kids that follow more rules than others. So an ideal gas doesn't actually exist. It's nothing. There's always going to be some little deviations here. There are some gases that behave more like ideal gases than others. Gases are going to behave most like an ideal gas when they're stored at low pressure and high temperature. The reason for this, when you store gas at low pressure, the particles can move very freely. And they have a lot of space between them. They can just do gas stuff. When we store them at a very high temperature, the particles are going to move rapidly. By moving rapidly, they're going to have the most gaseous behavior. We think of gases as being fast-moving particles. So those are the conditions under which gases are going to behave most like ideal gases. There are certain gases, there are certain examples of real gases. So when I say rich elements right here, these are actually real gases that behave most like ideal gases. And I just refer to these as the H gases. Hydrogen and helium behave most like ideal gases, and the reason for this is they have the smallest particles. So what we need to do, you need to actually know each part of the kinetic molecular theory and be able to relate it to real and ideal gases. For ideal gases, they're going to follow the rule completely. For real gases, they may or they may not. Gas particles are in a constant, random, straight line motion. To give you a little idea of what this looks like, we're going to be using this gas law simulator in class. The constant, random, straight line motion, what that's actually referring to is if you look at the particle that I have the red line on, it goes in a straight line unless it bounces off of something. It's moving constantly. It does not stop. Its path is in a straight line unless it hits something. Its path is random. It doesn't move toward any particular direction over another one. So it's moving constantly, randomly, and in general straight lines. A real gas does this, and obviously an ideal gas does this. So that is true for both of these. Number 2, gas particles are separated by great distances relative to their size. The volume of gas particles themselves is negligible. Remember, for an ideal gas, this is definitely true, so you can just go ahead and put a yes for that. In a real gas, the particles are far apart. I'm going to give this a sort of. So the particles are far apart. I buy that. However, the volume isn't really truly negligible. Imagine what would happen if you condensed down a sample of a gas. So just to give you a little bit of a visual using the simulator for this. Oops, opening the wrong window, sorry. If we move, oops, that's not going to work, sorry. If we move this down so that we're kind of crushing these particles into this bottom space here. If you imagine condensing this down, it would kind of be like condensing a gas into a liquid. The volume of those individual particles is, not negligible at that point anymore. So when we say something's negligible, it means it's completely able to be ignored. For the most part, we can kind of ignore the volume of the individual particles, but it isn't truly negligible. So that's sort of true. Gas particles have collisions that may result in a transfer of energy between particles, but the overall energy of the system remains constant. In other words, collisions are elastic. This is another nice one to look at on the simulator. The one particle that has the red line on it, you can see its velocity depicted right there with that little red guy. That actually will change a little bit. So if you put your eye on that particle for a minute, what you're going to notice is that particle's speed will occasionally change when it hits another particle. So right now it's going pretty quickly. It's going to eventually hit another particle, and when it does hit that other particle, it slowed down a little bit. Sometimes you'll even notice, if you look at this for long enough, that one of the particles will be going really slowly, it'll hit another one, and then they kind of exchange their energies. So when two particles bump into each other, it's going really slowly right now, that other fast one hit it, and there was that exchange of energy there. However, you'll also notice our overall temperature does not change. Temperature is our reading of energy in the system. So what this means is our collisions were indeed elastic. Okay, they were, particles were exchanging energy. So there's a transfer of energy between particles. The overall energy in the system, the temperature remained constant. Remember, this is going to be totally true for an ideal gas. For a real gas, there's no such thing as perfectly elastic. Because of a little something called friction, there's always going to be a little bit of energy loss there. So you don't really actually have completely perfect exchanges of energy. Gas particles have no attractive or repulsive forces between them. Totally true for an ideal gas. This is not true for a real gas. If this were true in real life, you would not be able to get a gas to become a liquid. You would not be able to condense it down to that state. So real gases do have what we call intermolecular forces of attraction between them, between the particles. But let's keep in mind, they are weak. So even though this doesn't work perfectly for real gases, it's not too far off. Those forces between the particles are very weak. And again, I just wanted to make sure that you kind of have an understanding of that elastic collision idea, which we did take a look at when we talked about this. Elastic collisions, remember, mean there's a perfect energy exchange, which doesn't really happen in real life.